Hi, good morning everybody. We start the quick revision program today for physics. We begin with the first chapter, units and measurements. Okay, let us start with the textbook. Units and measurements. First of all, we start with the different types of physical quantities. As all of you know, physical quantities are 7 in fundamental or base: mass, length, time, amount of substance. You try to tell with me. Luminous intensity, electric current, then thermodynamic, temperature. Different fundamental physical quantities have their own fundamental or base units. Also, there are two more supplementary quantities which are used for measurement of angles such as plane angle and solid angle. All this 7 plus to 9 base quantities, 7 fundamental, 2 supplementary. Based on all these quantities only, other quantities are derived, so-called derived quantities. Force, area, velocity, momentum, acceleration, energy. Second year we have learned magnetic flux. Very large number of quantities which are derived all based on fundamental quantities. Then derived quantities are made from fundamental quantities. Fundamental quantities are base quantities which cannot further be divided into smaller units. Okay. Basically, the system of unit what we use is an international units, that is called SI unit, international unit of system, that is SI unit. In SI system only we used to notate physical quantities. Here it gives you an idea on plane angle and solid angle. So let us discuss something about plane angle as well as solid angle. What is plane angle? Plane angle is that angle subtended by an arc of finite length at the center of the arc. Plane angle subtended at the center of a semicircle is pi radian. Its SI unit is radian. The equation what we used is angle is equal to arc divided by radius. So angle theta notation is equal to arc length divided by radius. If this represents an arc of length S and of radius R, the two extreme points of that arc describe an angular separation at the center of that arc, namely theta. Then theta is equal to S divided by R, or S is equal to R theta. And this one is very important. Angle is equal to arc divided by radius. In many of the problems, this equation is used. It is so particular to learn the units of angle. Unit of angle, SI unit of angle is, SI unit of plane angle is what? Radian. Radian. Sometimes it is written rad in some of the quantities. Radian. What is pi radian? Pi radian is equal to 180 degrees, and 1 radian is equal to 180 divided by pi degrees. 1 degree is equal to pi by 180 radian. All these conversions are important. Then some more units, smaller units are used. 1 degree is equal to 60 minutes. So 1 minute is equal to 1 by 60 degree. Okay, 1 degree 60 minutes. That is 60 minutes is equal to pi by 180 radian. So 1 minute is equal to pi by 180 divided by 60 radian. or pi by 180 multiplied by 60 in the denominator. Radian. Another smaller unit used is second. 1 second of arc is equal to 60 minutes. So 1 by 60 minutes. 1 by 60 minutes, or 1 minute is equal to 60 seconds. Therefore, we can convert 1 minute as 60 seconds, that is equal to pi divided by 180 into 60 radian. So 1 second is equal to pi divided by 180 into 60 radian. These ways we can convert second, minute, degree, radian. Okay, so that is important. Let us see that in our textbook. See that based on that many problems are there. Let us check few more situations there. Here it is mentioned in the solved example 2.1. Calculate the angle of 1 degree, 1 minute, 1 second of arc, sometimes called an arc second, in radian. In 2020, 2021 mains papers, all this arc second problems were asked. So that is important for competitive examinations also. And you can by heart all these results have been calculated by the textbook. 1 degree is equal to 1.745 into 10 to the power minus 2 radian. It is compulsory to by heart this. 1 degree equal to what? 1.745 into 10 power minus 2 radian. Then 1 minute is equal to 2.91 into 10 power minus 4 radian. 1 second is equal to 4.85 into 10 power minus 6 radian. Students, by heart all the three important results. Okay, let us see one solved example here. Moon is observed from two diametrically opposite points A and B on Earth. Angle theta subtended at Moon by two directions of observation is given 1 degree 54 minutes. Given diameter of Earth, compute the distance of Moon from Earth. Let me draw the necessary diagram for that. That's an important one. The question may be asked for competitive examination. And Moon is observed from diametrically opposite points. Let this be the line joining centers of Moon, small m, Earth, capital M. Moon is observed from two diametrically opposite points on Earth. And that points are namely A and B. Points are namely A and B. And these are those two lines which can be drawn from the two diametrical extremities of Earth onto Moon. The angle described at Moon is theta. Distance is small r. And this basis, this is called basis, is B. B is equal to the diameter of Earth. So angle theta is equal to arc, basis is arc length. Arc length is diameter divided by distance r. We can use tan theta here, approximations, because this angle theta is extremely small as the distance is much larger. That is why this method is used for measuring. This equation is the basic equation used for measuring large distances. Okay, that method which is used for measuring large distances is called a parallax method. And this angle sometimes called parallaxic angle. So angle is equal to arc by radius. So distance r is equal to diameter divided by angle theta. Diameter of Earth is given. Angle theta is given. Care should be taken for getting radial distance in meter. Diameter should be in meter. Angle theta should be in radian. That angle theta may be given in seconds of arc. That may be given in minutes of arc. Then we have to convert by using this relevant conversion equation that we have discussed before. 1 degree is 1.745 10 power minus 2 radian. 1 degree. Similarly, 1 minute is 2.9 10 power minus 4 radian. 1 second 4.85 10 power minus 6 radian. This conversions is made useful. Here, one thing else. Angle is given 1 degree 54 minute. That is to be converted into minute, okay, or second, then convert into degrees. For example, 1 degree 54 minute. 1 degree you can write as 60 minute. So 60 minute plus 54 minute is 114 minute. And 114 minute converted into seconds and converted into radian. Or else you can directly convert 114 minute into radian by using 1 minute conversion. So 2.91 into 10 power minus 4, you can readily multiply with 114 to convert itself into radian, right? And directly the solution. This is an important question for mains, NEET, almost all competitive examinations. It's very important. So students, don't forget to by heart all the three. What all are these to be by hearted? Conversion, degree, minute, second. Okay, degree, minute, and second. All these three conversions are important. Okay, see this, whatever we have discussed has been given here. Angle is equal to arc divided by radius. And parallaxic angle, you have to go through this tables also. Minute 60 seconds, hour 3600 seconds, all this in 1 year. How many seconds are there? 3.156 into 10 to the power 7 seconds. In 1 day, how many seconds? 86,400 seconds. By heart all that. Degree liter, conversion of liter is very important in forthcoming chapters. 1 liter is 10 to the power minus 3 meter cube or 1000 centimeter cube. Carat is important unit of mass. 200 milligram is 1 carat. Bar is an important unit of atmospheric pressure. 1 bar is 10 to the power 5 Pascal. Curie is an important unit of radioactive dose, which is written as 3.7, Curie. 3.7 into 10 to the power 10 per second. That's the unit of radioactivity, radioactive dose. Biggest unit is Curie. Another unit, Rontgen, is there. Rontgen 2.58 into 10 power minus 4 coulomb per kilogram. It is, the meaning is when 1 kilogram radioactive substance or 1 kilogram substance is exposed to what amount of radiation which can free 2.58 into 10 power minus 4 coulomb charge, electric charge. Rutherford is another unit. Rutherford, it's not mentioned here. Rutherford means 10 to the power 6 per second. Curie 3.7 into 10 power 10 per second. Rutherford only 10 power 6 per second. Rutherford. Barn is the smaller unit of area. 1 barn is 10 power minus 28 meter square. Barn is used for nuclear cross section. Then area hectare, air, all that used. Let us go through the rest of the topics. All this we have discussed. See, this one is an important problem. Sun's angular diameter is given in seconds. Distance given, what is the diameter of sun? It's very important in second 2020 paper. This similar question was there, but data was different. Same expression. With that, I have to tell you something more about the solid angle. What do you mean by solid angle? You consider a sphere of radius r. Sphere is of radius r. And you choose a differential surface, maybe a spherical cap, of area ds, defined at its surface, a small spherical cap you consider. Okay, so that you draw two lines like this. And it may be producing a right circular cone. Maybe producing a right circular cone. And this is a right circular cone. It has a curvilinear surface at the top. And the semi-vertical angle is theta. Half angle of that right circular cone is theta. You can define a new three-dimensional angle which can be subtended by all these lines joining center of that sphere and boundary of the spherical cap, boundary of that small spherical cap by an angle, three-dimensional angle called solid angle. Solid angle. That solid angle may be written as d omega. D omega. Let this small half angle may be known as d theta. D omega is the solid angle. Okay, by finding the area of the spherical cap, mathematically by integrating, you can find the correlation between this small half angle and also this angle d omega. And that relation is d omega is equal to the formula for solid angle, formula for surface area. You have learned, probably you have learned in mathematics, surface area of a spherical cap. Like that, d omega is equal to 2 pi into 1 minus cos theta, cos of d theta. Let me write that d theta as theta here. D omega is the small solid angle subtended at the center. D theta is the small semi-vertical angle. Semi-vertical angle or half angle of the right cone. I have written that as theta. So d omega equal to 2 pi into 1 minus cos theta. If theta is equal to 180 degree, you get d omega as 2 pi into 1 minus cos 180, 1 minus minus 1, that is 4 pi. If theta happens to be 180, this one also becomes 180. So 180 plus 180 becomes 360. That will be a sphere. So the solid angle at the center of a sphere is 4 pi. And its unit is steradian. Steradian. So unit of solid angle is steradian. It is written as SR. So it's important for mains. D omega equal to 2 pi into 1 minus cos theta. It is used in chapters optics as well as electrostatics in second year. While calculating electric flux in electrostatics and while calculating intensity of light coming out from a point source of light through some solid angle. What amount of light is falling on a given spherical cap, spherical surface or given area? What amount of light falls on a given area from a point source of light? Like that, problems are asked in mains examinations. Steradian is the SI unit of solid angle. So this conversion, which is not mentioned in textbook, but is asked often in competitive examinations. D omega equals 2 pi into 1 minus cos theta. 2019 mains paper, a question was asked regarding the surface area of the spherical cap. Surface area of the spherical cap can be easily found. Surface area is equal to 4 pi r square into 1 minus cos theta. 2 pi r square into 1 minus cos theta. Surface area, let the surface area be ds. ds is the surface area of the spherical cap. And that is 2 pi r square into 1 minus cos theta. And solid angle, so d omega can be written as ds divided by r square. So when you write ds by r square, you get the same equation 2 pi into 1 minus cos theta. And if theta is equal to 180, you get the surface area of the sphere 4 pi r square. Surface area of spherical cap is 4 pi r square for sphere, full sphere. For spherical cap alone, it is 2 pi r square into 1 minus cos theta. Then what is ds by 2 pi r square? ds by 2 pi r square is 1 minus cos theta. You can find out the surface area of whatever spherical cap by using this formula. So surface area of spherical cap, solid angle, plane angle relationship is very important. What is the solid angle subtended at the center of a sphere? That is 4 pi steradian. What is the solid angle subtended at the center of a half sphere? 2 pi steradian. Like that. It's very important topic. Now, estimation of size of a small molecule, it's not so relevant because no examinations, this calculation have been asked. Anyway, this formula you by heard, thickness of a film is equal to volume of the film divided by area of the film. You just go through that experiment, that's all. Okay, you read that experiment, then try to understand how to find out the thickness of that film by using this oleic acid experiment. You have learned it during class time. Now, length, mass and time measurements. Ranges of lengths. Biggest unit of length is parsec. 1 parsec is equal to 3.08 into 10 to the power 16 meter. Parsec is the distance at which average radius of Earth's orbit subtends an angle of 1 arc second. Let me explain that. Suppose Earth is revolving around the sun. Earth is revolving around sun. And this is that arc defined by Earth while revolution. Okay, and sun is here. Earth is revolving. And during its revolution of Earth around the sun in elliptical orbit, it goes from A to B. Suppose the distance measured from A to B is the mean distance between, average distance between Earth and sun. Earth moves along this arc-linear path, A to B. That distance A to B may be, say, the average distance of Earth and sun, mean distance of Earth and sun. That is called 1 astronomical unit. If this distance is 1 astronomical unit, then this angle is 1 second. Two conditions. This distance should be 1 astronomical unit, means mean distance between Earth and sun. And this angle should be 1 second of r. Then this distance is small r. And small r is equal to 1 parsec. So what is 1 parsec? 1 parsec is the distance between sun and Earth when Earth revolves around the fixed sun through a distance of 1 astronomical units, subtending an angle 1 second. Okay. If this angle is 2 seconds of r, if this angle is 2 seconds of arc for the same astronomical unit, previous question, that is a previous question, we can use angle is equal to arc divided by radius. For same astronomical unit distance, arc length will remain same, so theta proportional 1 by r, r proportional to 1 by theta. If theta doubles, r halved. So this distance will be half parsec for 2 seconds of arc. For 2 seconds of arc, that distance is 0.5 parsec. 1 second it is 1 parsec, provided arc distance should be 1 astronomical unit. അപ്പോൾ 1 astronomical unit ആണ് ആ ആർക്കിന്റെ നീളമെങ്കിൽ 1 സെക്കൻഡ് ആണ് സബ്ടെൻഡ് ചെയ്യുന്ന ആംഗിൾ എങ്കിൽ സണ്ണും എർത്തും തമ്മിൽ അപ്പോഴത്തെ ഡിസ്റ്റൻസ് 1 പാഴ്സെക് ആണ്. അതേസമയം 1 astronomical unit ആണ് എർത്ത് സണ്ണിനെ ചുറ്റി സഞ്ചരിച്ച ദൂരമെങ്കിൽ സണ്ണിൽ സബ്ടെൻഡ് ചെയ്യുന്ന ആംഗിൾ 2 സെക്കൻഡ് ആണ് എങ്കിൽ ഈ ഡിസ്റ്റൻസ് അര പാഴ്സെക് ആയിരിക്കും. ഓക്കെ, അത് കാണാതെ പഠിക്കും. ഓക്കെ, that's the biggest unit of distance is parsec. Another one is astronomical unit. that is 1.496 into 10 power 11 light year. Distance traveled by light in 1 year, that is 9.46 into 10 power 15 meter. Astronomical unit is the average distance between sun and earth. Okay. Then measurement of smaller units, Fermi, angstrom, all this you have to go through. There's a table in textbook. You go through that table to by heart all these prefixes. Unified atomic mass unit is used for measurement of mass, length, time, all these measurements have to be discussed. One unified atomic mass unit is defined as 1 by 12th of mass of carbon 12 atom. 1 by 12th of mass of carbon 12 atom, and is clearly 1.66 into 10 power minus 27 kilogram. Then size of a proton, this table worth to be noted. Size of a proton 10 power minus 15. Distance to the boundary of the observable universe 10 power 26. Size of atomic nucleus 10 to the power minus 14. The sizes are to be roughly seen, need not by heart, but maybe for competitive examination there may be options. So size of proton is very close to 10 power minus 15 meter. That is the order of magnitude. So order of magnitude of size of proton may be asked. That is also asked. Order of magnitude of size of proton is minus 15. Order of magnitude of size of electron. What is the order of magnitude of size of electron? It is not written here. Order of magnitude of size of electron. That will be much lesser than size of proton. Size of atomic nucleus 10 power minus 14 meter. All this. Now, moving to the next page. Electron. See, mass of electrons order is mentioned as minus 30. Mass of proton minus 27. Order of magnitude, better you by heart order of magnitudes. A Boeing aircraft. Order of mass is 8. Mass of moon 23, earth 25, sun 30, Milky Way galaxy 41, observable universe 55. Then measurement of time, atomic clocks. Cesium clocks are used for measurement of precise time. Ratio of largest and smallest masses of objects in our universe 10 power 41 whole square. It's an interesting thing to observe. Okay, there's a coincidence between these large and small numbers. That's very important to be noted, maybe asked in exams. 10 power 41 square. See another one. Ratio of longest and shortest lengths of objects in our universe about 10 power 41. Ratio of longest and shortest time intervals also 10 power 41. But ratio of longest and smallest, largest and smallest masses is 10 power 41 square. So that 10 power 41 has something to tell. Still people do not know what is that. What is the relationship? How that relationship comes out to be? Is there anything peculiar which brings that result so? That's why it is so curious for scientists to know about how that things come out to be. There is somebody is there who have engineered all these things. We do not know how that has come. Anyway, that is a result. In future, we may expect a conclusion regarding all this. We may get some result based on that. Now, we have to move to another topic. Accuracy, precision, errors in measurement. Accuracy, precision, errors. How do you differentiate between all these? Accuracy, precision, errors. What do you mean by accuracy? Accuracy means the closeness of result with true value. Accuracy refers to closeness of result with true value. Then what is precision? Precision is not referred to the closeness of result with true value, but it is the precision with which that measurement is being taken. Accuracy, it's not accuracy. Preciseness, resolution. With what resolution that measurement has been taken. That is precision. But accuracy is to tell something else. The degree of closeness of the observed value with the true value is called accuracy. That's the difference between accuracy and precision. Let me tell you one example for that. Suppose a person A measures acceleration due to gravity at a place on earth as 9.87 meter per second square. Another person measures 7.87643 meter per second square. By watching into these two, the average value, G mean value of earth surface 9.8 meter per second square, it is given. That is the taken as the true value. Arithmetic mean is taken as the true value. And that is noted. Let us compare the measurements noted by A as well as B. What do you say? Which one is more accurate? Answer me. Which is more accurate? One may say that the one which has more number of significant figures is more accurate. But that would have been accurate if true value was not known. But if true value is known to you, true value is 9.8, B is less accurate. But A is more accurate. Can you say why? Because B has a recorded value which is very close to true value. What happened to B? B has got a sophisticated technology, a sophisticated instrument. Maybe B may be a rich person and may have bought a sophisticated instrument to measure the value of G at that place to this much of significant figures, but no use. Why? He has made a less accurate result, but he has more precision. That precision may be due to the device which may have got smallest least count, because he could measure up to more number of decimal places, but A could not measure up to large number of decimal places because he has got a device which has got large least count. So when least count is more, precision is less. That is why A is less precise. B is more precise. B is more precise and less accurate. A is less precise and more accurate. This type of questions may be expected for Neet, mains as well as KVPY. All these examinations, this type of questions are important because these days competitive examinations are only based on theory questions. So A as well as B measures these quantities differently. One is precise, the other is accurate, right? Let us go for the next topic. Precision and accuracy. Hope that you are clear with precision and accuracy. Once again, we have done all this. Better you go through all these tables regarding ranges of order of time intervals. All the tables mentioned in textbook are to be noted. Okay, now we move to other topic, which is significant figures, order of magnitude, all that. Okay, after that we will come back to these errors. Okay, right? Accuracy, precision, all that we have discussed so far, then we can make use of significant figures and all. What do you mean by significant figures? Significant figures are the number of figures, digits, known reliably about one measurement, plus the first digit, that is uncertain. Uncertainty produced through different number of digits, but the first digit only taken as significant. All non-zero digits are significant. All non-zero digits are significant. 5, 4, 2, 1 has How many significant figures? 4. Let us give you examples. 5 or 2. 1 has 4 significant figures because all non-zero digits are significant. Now 5, 0, 2, 1 has also 5 significant figures. Not 4, but 5. This 0, as it comes between two non-zero digits, are also significant. To any 0 coming between two non-zero digits are also significant. Okay. Next example. 5500 meter. If somebody says like this, we say that there are only 2 significant figures with the 2 zeros ambiguous. These trailing zeros without decimal point are called ambiguous zeros. Trailing zeros without decimal point are called ambiguous zeros. How many significant figures are here now? 2 significant figures with the 2 trailing zeros as ambiguous zeros. But if you have trailing zeros followed by decimal point, they are to be taken as significant. So there are 4 number of significant figures. Here trailing zeros are there, but trailing zeros are followed by a decimal point. That's why they are to be taken significant. Let us apply a few more examples. 50.01 centimeter has how many significant figures? 1, 2, 3, 4. All these 2 zeros are also significant. Zeros coming in between non-zero digits significant. Now 0.074 meter. How many significant figures? There are only 2. You are right. Very good. The first 0 insignificant. The next 0 is insignificant. Why? Because the 0 is followed by decimal point, but before that there are no non-zero digits. For example, 1.074 meter. How many are there? 4. Oh, excellent. Very good. 4. This 0 is not. That 0 is significant because that is followed by a decimal point. Also to the left of that decimal point, there is a non-zero digit. Okay, hope that you are clear with this idea. Now, how to round off quantities? While rounding off with the proper number of significant figures, we have to learn that also. For example, 5, 4, 3, 2, 7, 5 meter. 1, 2, 3, 4, 5, 6. There are 6 significant figures. Round off it to 5 significant figures. Then, starting from the very first one, which is called the most significant digit 5. Next most one is 4. Next most is 3. Next one is 2. I have to round off to 5 significant figures. I have to round off to 5 significant figures. This number. Then next one is 7. Next one is 7. And 5 is to be dropped one. 5 is to be dropped. 5 is to be dropped. Then I have to see as 5 comes. After that, no digits. So 5 followed by all zeros. 5 rule tells like that. After 5, no digits are there. All zeros only. Nothing is there. So 5 followed by all zeros. Then you have to see the preceding digit. This is called the preceding digit. Preceding. That preceding digit is odd or even. That is odd. As the preceding digit is an odd one, you raise it by 1, then 8. So 5, 4, 3, 2, 8. Okay. Into 10 to the power 1. Because I should not lose the size, amplitude or magnitude of that quantity. I should not lose for getting the idea of precision or significant figures or accuracy, whatever. For accuracy, we should not lose the actual size of that measurement. Okay, this can be written as, say, 5.4328 into 10 to the power 1 is already there. Then into 10 to the power. The decimal was where? Here, 1, 2, 3, 4. 4 units to the left, you add 4 here. If 4 unit to the right, you write minus 4. 4 units to the left if decimal moves, plus 4. To the right, minus 4. Okay, that is 5.4328 into 10 to the power 5 meter is the expression scientifically. You should not express like this. You should not express like this. You should only express that notation scientifically. Now it is scientific. When it is expressed in scientific notation, you can find order of magnitude. What is the order of magnitude? Order of magnitude of this number is not 5. It should be 5 plus 1, that is equal to 6. 5 plus 1. Because the most significant digit is 5 followed by not all zeros. Then you round it off to the next prior digit. So 5.4328 is written. So 5 point. First digit is 5. Most significant digit is 5 followed by not all zeros. Then you raise it by 1. So 5 plus 1 is equal to 6 is the order of magnitude of this number. Like this, let me exemplify. Mass of electron is equal to 9.1 into 10 power minus 31 kilogram. What is the order of magnitude? Wrongly, children may write minus 31, but it should be minus 31 plus 1 because the most significant digit is greater than 5. If most significant digit is greater than 5, raise the order by 1 with the power of 10. This is the method. Mass of proton, but 1.767 into 10 to the power minus 27 kilogram. Here order is only minus 27. Order is only minus 27 because the first significant, most significant digit is less than 5. Then you choose the power of 10 only as the order. Okay. 5,890 angstrom. What is the order of magnitude? Order of magnitude while finding care should be taken. This without losing the bigness of that number, you express it in power of 10. 5.890. See, decimal was here. 1, 2, 3. 3 units to the left. Multiply. Tell me what should be written. 1, 2, 3. What should be written? Plus 3 or minus 3? As I told, when decimal moves towards left, you should write plus 3. If decimal moves, decimal is to be moved to the right. I will exemplify that also. Angstrom. Okay. Now what is the order of magnitude? 3. Is it correct? No, it's incorrect because most significant digit is greater than 5. Then add by 1. Then order of magnitude is 4. Care should be taken while finding out order of magnitude. You should not convert system of unit. When you change the system of unit, order of magnitude changes. Changing system of unit, order of magnitude changes. Important. Changing system of unit, order of magnitude changes. Unless otherwise specified, you strictly stick on to the same quantity unit as it is and find out the as it is. 0.745 into 10 power minus 3 kilometer. How to find the order? For this, it can be written as 7.45 into 10 to the power minus 3 is already there, right? Can you guess what should we do? Decimal point is to be shifted from this point to the right by 1 unit. Decimal point 1 unit to the right. Then you subtract 1. That is 7.45 into 10 to the power minus 4. That much of kilometer. Now what is the order? Is it minus 4? Again missing. Incorrect. Minus mark. It is not minus 4 because the most significant digit is greater than 5. That is plus 1. So answer should be minus 4 plus 1 minus 3 is the order of magnitude. This is the way. I hope that children you are clear. Sometimes you may write 5,000 meter. You never express like this. It is a wrong way to write all this. You have to write either 5.000 meter, like this. Then it is correct. No zeros are ambiguous. You should not lead any ambiguity to express results. You should not transfer ambiguities while measuring. Okay, that is the way of science. Clarity. 5.000 meter is correct. How many significant figures are there? 4 significant figures are there. While writing like this, you can only assign one significant figure and 3 zeros ambiguous. That is incorrect. 5.000 meter. 4. While writing like this, you can clearly get an idea of the precision of the measuring instrument. What is the precision or what is the least count of the measuring instrument? 0.001 meter is the least count of the measuring instrument. As the least count is lessened, 0.001 means precision is more, hence accuracy is also more as the true value is not given. But if true value is given, accuracy is that which is close to true value. Okay, that is mentioned in that acceleration due to gravity example. Okay, so 5.000 meter, how many significant figures? 4. 5,000, how many significant figures? Only 1. 3 zeros ambiguous. Okay, what is the order of magnitude of 5.000 meter? Order of magnitude of 5.00 meter. Order of magnitude is written as 5 into 10 to the power 1. That's all. 5 into 10 to the power 1. This can be written as 5 into 10 power 1. What is the order? 1. Is it correct? 5.000. All zeros followed by all zeros. Okay, what is the order? 1. But if it was 5.001 meter, what is the order? Order is equal to 5 plus 1. That is equal to 6. Because most significant digit is 5 followed by not all zeros. But here most significant digit is 5 followed by all zeros. That is why 4 is the number of significant figures. SF is 4. Order is 1. But here SF is still 4 remaining same, but order has increased by 1. All this may be asked for mains also, NEET also. 5.00 person measures 5.000 meter, another person measures next time 5.001 meter. In this process of changing the result, significant figures remaining same, order does not remain same. Significant figures remain same, order increases by 1. Okay, significant figures increases by 1, order doesn't change. Like this, many options or statement type questions. This is the way by these days examination question papers are seen. That's very, very important to learn the theory very well. Okay, not only by practicing previous papers. Okay, you have to practice previous papers definitely for the last 3 years at least. Then you move with this theory part very clearly. Okay. Now, let us choose the topics what we have not touched. Let us move this chapter text-wise. Here, different types of errors mentioned. What are the different types of errors? The errors can be classified into systematic as well as random in a broad sense. Systematic errors are systematically introduced. Instrumental error is one based on instrument. Zero error is an instrumental error. Zero error. Imperfection in technique, experimental procedure is another one. Personal error is another one that is based on personal biasing. Random error cannot be predicted how it establishes. It goes randomly, regularly. We do not know how it is established. But random error can be minimized by taking more number of observations. More the number of observation, less is the random error. You just go through this part is also important. You read, that part is important. Now least count error is a different one. It's measured differently. Least count error occurs because of different instruments. Different instruments have got different least counts, hence different least count errors. For example, screw gauge has got lesser least count error because its least count is less. That depends on the resolution of that instrument. Different instrument like vernier calipers, meter scale, screw gauge, all these have got different least counts, hence different least count errors. Okay, screw gauge has got lesser least count error than that of meter scale. The interval after which measurements have been taken in each of these measurements or devices are different. Meter scale has got a precision of 1 millimeter or 0.1 centimeter. Vernier has got a precision of 0.01 centimeter. Screw gauge has got 0.001 centimeter. More precise with screw gauge because least count is less. When least count is less, then precision is more. Okay, but sometimes, most probably, when true value is given, accuracy is one which is measured differently. Accuracy is close to true value. Accurate measurement is much close to true value. Now, how to mathematically measure all these errors? First one is an absolute error. How to measure absolute error? Any quantity can be expressed within proper error limits. While measuring taking a measurement and expressing it that as a result, when we express as a result mathematically, we have to express that within proper error limits. Okay, for that we have to know the true value. How to know the true value? Take arithmetic mean. That is mentioned here. If A1, A2, A3, A4, etc. are the observed values of a given measurement, arithmetic mean is A1 plus A2 plus A3 plus etc. plus AN all divided by. That is arithmetic mean. Then we have to find out the standard deviations of arithmetic mean from the true values. That called deviations. Each of those deviations are mentioned as delta A1, A1 minus A mean. Delta A2, deviation of the second observation with the true value. A2 minus A mean, continuing. But these deviations can be positive or sometimes negative. Suppose we have three measurements, 1, 2 and 3. Mean is 2. Okay, what is the first deviation? 1 minus 2 minus 1. Second deviation, 2 minus 2, 0. Third deviation, what is the third deviation? 3 minus 2, 1. So deviations were minus 1, 0, then plus 1. So deviation of any observed value from the true value or mean value may be positive, may be negative, may be 0. 0 not necessarily, but surely it is positive and negative. Sometimes 0. Then we have to take modulus of all these deviations. Take modulus of all these deviations. Then take the arithmetic mean of all these deviations. Moduli of deviations. Arithmetic mean of moduli of all these deviations called delta M mean. That is called mean absolute error. So mean absolute error is the arithmetic mean of all the moduli of deviations. Deviation may be called absolute error. Okay, deviation may be positive or negative. But absolute error can never be negative. Absolute error can never be negative. Arithmetic mean of all these absolute errors is called mean absolute error. Right? Delta A mean. Now, how to express this in percentage? Whatever we get, examination mark, whatever we get, we have to express in percentage. Then only we have to know we will know the relative size of that measurement. Here, how to express that measured error in percentage. For that, the change, that means mean absolute error, you divide by the true value. Mean absolute error divided by true value is called what? Relative error. Multiply by 100 simply to get the percentage error, right? Very important. How these measurements have been taken into calculation of any of the quantities or errors, how to express this errors in combination, in addition, multiplication, subtraction, division, all these are to be discussed now. Before that, let me go through this example. It's very important. 2020 mains paper, similar question was asked. Only slight changes were there in values. That's a very popular question. You can try this one. Don't forget to by heart this method. See, we measure the period of oscillation of a pendulum. Okay, and the readings turn out to be given. Calculate absolute error, relative error, percentage error. See, period while measuring, we have to first of all find the true value. Oh, add all this divided by the number of observations 5. Then you get 13.12 by 5. Try to calculate that by yourself. Need not refer this. Then 2.624 seconds. The accuracy is 0.01 seconds. Accuracy is of the order of 0.01 seconds. See, the accuracy is of the order of 0.01 seconds because that time interval measured in steps of 0.01 seconds. 0.01, 0.02, 0.03, 0.04. I don't know, do not have time to read all this. Like that, it comes 0.99. Then last, it gets 2.62, so 2.63, though, so it measures in steps of 0.01 seconds. So what's the accuracy? 0.01. So it should be expressed in 2 decimal places only. Okay, that's why 2.624 we discard the third significant digit 4. Actually, there are 4 significant figures, but we have only precision up to 2 decimal places. Okay, taking the precision up to 2 decimal places, now we have to express that time in 3 significant figures. That's why only we took 2.62, the last digit dropped. Okay, then error. What are deviations? Deviation is positive, other deviation is positive, negative, negative, positive, positive. So positive and negative deviations are there. Take modulus of all those and take arithmetic mean. You get the mean value. That is 0.11 seconds. Still you have to maintain the 2 decimal places there. It's already maintained. Then 2.62 plus or minus 0.11 can be written. How to express that in percentage? It's not expressed here. Let us express in percentage. How to express that in percentage? For expressing in percentage, we can use this one like this. Delta T mean divided by T mean. That is equal to delta T mean is how much? 0.1. 0.1 divided by, what is the time? 2.6. So 0.1 by 2.6 into 100 will you get the percentage error. So convert into percentage error, mean absolute error divided by true value multiplied by 100. Okay. Period of oscillation is given 2.62 plus or minus 0.11. So lies between 2.62 plus 0.11 and 2.62 minus 0.11. Between 2.73 and 2.51. That is the accuracy. Okay, as the arithmetic mean of all the absolute errors is 0.11 second, there is already an error in the 10th of a second. Hence, there is no point in giving the period to 100. That's why it is written 0.1 seconds. Okay, so while expressing final result, you can only express as 2.6. Arithmetic mean is taken as 2.6, not to the next digit. Okay, deleting the next digit, which was written earlier as 2.62, we came to know that it is only true for 1 significant figure while expressing error and 2 significant figures while expressing the true value. The relative error is 0.1 divided by 2.6 into 100, that is for percentage error. So what is the relative error expressed in percentage? That is 4%, right? Now combination of errors. How the errors are being propagated. Errors are being propagated differently in different measurements. In sum of 2 quantities A and B, that is equal to A plus B. Let me write it there. in a board. If you write Z is equal to A plus B, delta Z, absolute error is equal to delta A plus delta B. If Z is equal to A minus B, delta Z is equal to delta A plus delta B, still it is plus. So if quantities are to be added or subtracted, absolute errors are to be added. How to find out the relative error in sum or difference? Delta Z by Z is equal to delta A plus delta B divided by A plus B. If it is A plus B, if the measurement is Z is equal to A plus B, and if the measurement is Z is equal to A minus B, you get delta Z by Z is equal to delta A minus delta B divided by A plus B. Is it true or false? It is false. It is false. How to write it? Delta A plus delta B divided by A minus B. It's correct. Very good. Delta A plus delta B is the sum of absolute errors. So sum of absolute errors divided by the difference of that quantities will give you relative error in difference of two quantities. So relative error in difference of two quantities is the ratio of sum of absolute errors and their difference. Like this statement type questions will be asked. Z is equal to A plus B means Z is the sum of A and B. In sum of two quantities, their absolute error is the sum of in absolute errors of each. Z equal to A plus B, delta Z equal to delta A plus delta B. If Z is equal to AB, what is delta Z? Delta Z by Z is equal to delta A by A plus delta B by B. That is correct. Then delta Z is equal to Z into, Z can be written as AB into delta A by A plus AB into delta B by B. You can cancel A here and B here. You get what? You get delta Z as A delta B plus B delta A. This is very important, may be asked. So Z equal to AB. Z is written as product of A and B. Okay, whenever you express a product, relative error is the sum of their relative errors. Percentage error is the sum of percentage errors. Okay, but absolute error is not taught like that. Absolute error is equal to B into delta A plus A into delta B. That's very important. Okay, similarly in ratio also you can get the relative error as it is. Follow accordingly. Okay, delta Z by Z equal to delta A by A plus delta B by B in ratio also. Okay, so this is also important. This type of questions you may practice. Solved examples are very important. Okay, resistances in series. R is equal to R1 plus R2. There is a sum. But in parallel combination, you have to use this equation, the differential equation. 1 by R equal to 1 by R1 plus 1 by R2. Take the first derivative. Then you get this equation. Relative error in Z is equal to A raised to 4, B raised to 1 by 3, CD raised to 3 by 2. That problem is also important. Whenever you get combinations of errors, for example, Z is equal to A raised to 4, B raised to half, divided by C cube, all this. Delta Z by Z is equal to 4 times delta A by A plus 1 by 2 times delta B by B. Then what? Plus 3 times delta C by C. All this. This is the way by which you have to get errors. Okay. Now, this question is also worth noted. Period is given. What is the value? Accuracy in determination of G. In determination of G, you have to write G equal to 4 pi L by T square, 4 pi square L by T square. Then delta G by G is equal to 4 pi square does not have any error. Delta L by L plus 2 times delta T by T. Okay. While measuring T here, it's very important to note that time for that many number of oscillations. 100 oscillations time were measured using the experiment. The time measured was 90 seconds. That is why here you have to write the number of oscillation time required. 100 oscillation time required is 90. So this problem is also very important. And the significant figures part we have already revised. Go through the rules as well as few more examples. Rounding off, order of magnitude, all this we have learned. The only topic left is dimensional analysis. What is the dimensional analysis meaning? Every derived quantities may be expressed as fundamental quantities. Every derived quantities can be expressed as in powers of fundamental quantities. Okay, the power of fundamental quantities expressed in a given derived quantity, that power is called dimension. So the dimension of force is mLT raised to minus 2, means dimension of mass in force is 1, dimension of length in force is 1, dimension of time in force is minus 2. Like that we can come to know what power is assumed by each of those derived quantities in fundamental quantities. Okay, one of the applications, very popular application I will tell you, if power is a constant, given power is a constant, dimensional method can be applied mathematically like this. If power is a constant, how? Distance varies with the time. If you wanted to know power is a constant, given power is a constant. It's a very popular question and that is mentioned in chapter work power energy at the end as an objective question by NCERT. Power is a constant is given constant power. So dimension of power, what's the dimension of power? M, power is energy by time, m L square T raised to minus 3. Power is a constant, it is given. Okay, a body is moving with constant power. The mass of that body is a constant. That is, power is also constant. So L square T raised to minus 3 is a constant. Then L square proportional to T cube, L proportional T raised to 3 by 2. You may take more time by using a calculus method, it's difficult. But this method, a dimensional method, will lead to a very simple result quickly. So L proportional T raised to x by 2, where x is 3. L proportional to T raised to 1 by 2, T raised to minus 3 by 2, all that given. But in option T raised to 3 by 2 is only correct. From this we can easily find out what is a velocity dependence. Velocity means length by time. So divide this by time. So T raised to 3 by 2 minus 1. That is T raised to 1 by 2. That is velocity proportional to root T. Similarly, you follow with acceleration, force, momentum. All this you can unveil from this method. So dimensional method is very important. Can be used for deriving physical quantities among one another. We have already derived a time period of pendulum. You can refer that example. NCERT it is solved. Another one is relationship between SI and CGS quantities. SI CGS conversion. You can make use of this dimensional method. Another one is you can check the correctness of all equations. If any equation is physically correct, that should be dimensionally correct. Okay, any equation dimensionally incorrect is incorrect. Any equation dimensionally incorrect is never correct. Okay, but if any equation is physically correct, you see, any equation is physically correct, that should be dimensionally correct. But if any equation is dimensionally correct, that need not be physically correct. But if any equation is dimensionally incorrect, that equation is physically incorrect. So for physical correctness, dimensional correctness is a must. But if any equation is dimensionally correct, that need not be physically correct. For example, V is equal to 2U plus A by 2T if something is like this. We know it is very common relation. Somebody has made a mistake and wrote 2U plus half AT like this. Anyway, V equal to U plus AT is used, a kinematic equation for constant acceleration, very popular one. But some useless fellows made some mistakes and written like this. Okay, but dimensionally when you check, we cannot find any problem there. And we say that that equation is correct dimensionally, but physically that equation is incorrect. Dimensional correctness is not a thing which can decide whether it is physically correct or not. But if an equation is dimensionally incorrect, for example, v square is equal to u plus at, you try dimensionally, dimension of each terms should be same, but here each terms will give different dimensions. That's why this equation is dimensionally incorrect. That's why this cannot be physically correct. But the first equation, whatever I have written, is dimensionally correct, but still physically incorrect. So if any equation is dimensionally incorrect, that cannot be physically correct. But if any equation is dimensionally correct, that need not be physically correct. So this important thing is maybe tested as a statement type question in your paper. Okay. So all these things are very important, particularly dealing with dimensions. Also, we have lots of time required for explaining the sample exercises for dimensions. You just go through all that we have done, go through previous papers, 3-year previous papers for and trying to understand the methods of questions here. The major principle of homogeneity of dimensions. Each and every terms of a physical equation should have same dimensions. Okay. Dimensions of every term should be same. That's the application of dimensional analysis. Also, care should be taken going through the exercises behind as well as summary. Summary points to ponder. All these are important. Okay. These questions, backside questions are also important. Okay, we have tried within this short time interval, we have tried to include maximum important topics as examination point of view in physics. Okay, let us conclude. Next, we'll be meeting soon with the next paper. Thank you. Thank you very much.